Hi everyone, my name is Shaborn Isaac Berry from Berry Science Lab, and welcome back to Quantum Mechanics. Today we're going to be talking about blackbody radiation and ultraviolet catastrophe. We've already done a lecture on it, well, two lectures on it actually, but I wanted to condense those into one. So, we're going to be talking about the backstory to quantum mechanics and what caused it. So, what did? Well, it all started with Newton's corpuscular theory. You see, in the 1670s, there wasn't many studies that could have been done on light. Newton was more focused on the qualitative side of things. The study of light, his studies on light were published in his book, Optics. And in it, he described light as probably being made of several tiny particles. He described a new force that was acting on them, a fundamental force. Some materials, like glass, would repel these small corpuscles, corpuscle being the word for small body in Latin, which would cause them to reflect as he observed. Other materials would attract them, like the transition from air to water. An attraction that would subsequently change its direction, which is how he explained refraction. These were most of the tests he did at the time, and this was also the way he explained his own prism test, where he took one ray of light and split it into six. Well, there were actually infinitely many rays of light, but he saw six distinct colors coming out. I've only drawn four because I don't have space for more. And this dividing line was explained by him as well. White is just a mix of all of those kinds of corpuscles, but they travel, they have sort of different corpuscular masses. So materials that attract and repel them will do so with different rates. And so that means the red corpuscles will take a different path than the yellow corpuscles. And so refraction was explained. Now, there still was one thing that was yet to be explained. Sometimes he observed, well, he didn't observe this specifically, but light can be observed to both reflect and refract, in fact, split off into two different rays with the same exact color on the same exact material. Newton didn't explain this because that would require the glass interface to both be repulsive, as he described with the case of reflection, and attractive, as he described in the case of refraction. So this is the corpuscular theory. But of course, it's very imperfect. Not only could it not explain the very simple phenomenon, the corpuscles never seem to bump into one another or collide. So what would happen when they did? And finally, it couldn't explain diffraction, but diffraction wasn't observed by him at the time. It was only much later, in 1799, when Thomas Young conducted what's now known as Young's experiment. First, he took a box filled with water. This was his experimental apparatus. And what he did was he took the water, don't mind that it's red colored water, I don't have blue chalk, and he filtered it, essentially. He put up one wall inside the box that had two holes, slits, which the water could go through. And then, at the other end, he set up a detector to detect the intensity of the incoming water waves. So, for an easier top-down view, you could view it like this. A wall with two holes and a detector. The water waves would emerge from whatever disturbance Young made, and it would be forced to go through these holes. Slowly, these waves would interfere with one another, sometimes adding to each other's intensity, sometimes subtracting. And by the time they reached the detector, they formed a pattern of light fringes, not light fringes, but fringes of high and low, and higher and low, and higher and low, and the highest around the midpoint, then lower, low, lower, low, and lower. So there's this nice pattern for water. He studied this pattern in depth. But the insight that he had that a lot of others didn't was, what if I just do the same experiment, but instead of filling a box with water, I take this wall with two slits and shine light on the other end. What he found was that when light was shown, what he detected on the other end was, obviously he didn't have flashlights, he did this with candlelight fire or equivalent, the same exact bright, dark, brighter, dark, brighter, dark, brighter, dark, brightest, then less bright, dark, less bright, dark, less bright, dark, less bright, dark. So, as you can see, it formed the exact same pattern as the water did. They're the exact same pattern. So the fringes that light made were exactly the same as the fringes that a wave made. So light has to be a wave, right? And of course, it's not equivalent to the fringes that any bullet, when shot through the hole, would make. As you might expect, if you just shoot particles through this hole, you'll just get one big fringe near the top and a bunch of decaying fringes near the bottom, maybe with small peaks directly in front of the holes. So that means that light is not made of corpuscles. Well, at least not at the time. They were waves. And so, Young conjectured, Newton was wrong. The corpuscular theory was dead. light was a wave, and it never did act like a particle. This also explained diffraction, and it explained why it never seemed to collide with itself. And it explained all of its reflective and refractive properties in slightly different ways. Now it seemed light was finally understood. Until another century passed. Because by 1899, a challenge had stood up. Now, one very common subject of study at the time was what happens if you have light and you trap it in a box of finite volume. Sometimes it will bounce in there chaotically, and other times it will form self-repeating patterns. Called radiation modes. Now that's a very simple way to describe modes, but they act essentially like normal modes. And the question was, how many ways or how many radiation modes are there for light of a particular frequency, and frequency is represented by nu, for some light trapped inside a box of volume V? The answer to that came in the form of the Raleigh Gene Law. How is it derived? Well, first, you take this equation that describes light's behavior in a cavity. Now, if we take this cavity to be rectangular, which is a fine approximation, what we can say is that, well, we're going to first use separation of variables, which if you watch quantum mechanics series, you'll see this is one of our favorite techniques. X prime prime y zt plus y prime prime x zt plus z prime prime y zt minus 1 over c squared t prime prime xyz is equal to 0. Now we can divide both ends by xyzt. Now this cancels with totally different things for every term, but you're left with x prime prime over x, y prime prime over y, z prime prime over z, minus 1 over c squared t prime prime over t. Now what you can do is you can move some of these to the other side. If, for example, you want to isolate x, you can move everything not containing x to the other side. And now here's what you'll notice. What you'll notice is that everything here is a function of x, and everything here is not a function of x. It's a function of y, z, and t. These two don't share a variable. So if I take the partial derivative with respect to x of both sides, this is going to give me the partial derivative of this, and this is going to give me 0. Hence, this side is a constant. And hence, since this is equal to that side, this side is also a constant. That's a really great technique. So what we're going to do is set it equal to a separation constant. In x's case, kx. But if we chose to isolate y instead, we could call it ky. Z, we could call it kz. And in t is a special case because it's time, it's not a spatial dimension. We call it the frequency. So let's call this kx squared. Then x prime prime over x is equal to kx squared. And what does that give us? X prime prime is equal to kx squared x. And so x is equal to one of two things. It could be ekxx, or it could be something of the form a sine kxx plus b cosine kxx. And of course, this could have some coefficient too. And this holds for every other function. But then we get to boundary conditions. No? Boundary conditions tell us that if we want a continuous distribution, the light is never going to escape our box, which means it's never going to hit the boundaries of our box. It's never going to be inside the box's cell. It's always going to be stuck inside the box, not in the box. Oh, how do I describe this? It's not going to be wedged into the cardboard. It's going to be stuck in the cardboard. So then that means it will never have x is equal to 0, because that would describe this face of the box, and it'll never be there. Same thing with y of 0. It will never be there. So the light energy that's going to be stored in there is going to be 0. Same thing with z. And, of course, the box has other boundaries. Oh crap, this is not z equals 0. Z is this side. The box has other boundaries. We can say its length is Lx, its width is Ly, and its height is Lz. Then x of Lx is 0, x of Ly is 0, y of Ly is 0, and z of Lz is 0. P of 0 is also 0, but there's no other restriction. Now notice something here. An exponential is never going to be 0 unless you add a constant to it. And I don't see a constant here. We can't actually add a constant to the solution because it would contribute to this side and not this side. So that means the exponential term will go to waste. And the cosine term will also go to waste because it's equal to 1 when x is equal to 0. The only thing that remains is sine, because sine is equal to 0. Once we have that, so since sine of 0 is equal to 0, we can keep this around, which means I'm going to set x is equal to sine kxx. Sure, it could have an amplitude, but I don't particularly care about it for now. Then y could have the same thing. Y is equal to sine ky y. Z is equal to sine kzz. But now notice something. When is sine equal to 0, as dictated by these boundary conditions? Well, whenever whatever's inside the expression is some multiple of pi, integer multiple, which means kxx is an integral multiple of pi. And so it is with kyy and kzz. Time is a little bit different. If we solve the differential equation for time, we're going to be totally sidelined by this, but this is going to be, well, omega squared t. T is just going to be c e to the omega t plus a sine omega t plus b cosine omega t. And as you can imagine, everything also disappears except for sine omega t. So, in this case, oh crap. Okay. Hold on for a second. What is omega, actually? I think we should probably address that. we're not just going to brainlessly write omega, or are we? Sorry. We get 1 over c squared t prime prime is equal to omega squared t. So I mean, what is omega then? T prime prime is equal to c squared omega squared t. So t is equal to sine c omega t. Kind of ridiculous, isn't it? So, back to the subject. Oh, why would I write this? Sorry. Kx Lx Ky Ly Kz Lz is equal to this. Which means what? Well, nx is equal to kx Lx over pi, and y is equal to the same thing, and z is equal to the same thing. Now we can also pursue something interesting. What we're going to do is show that n is actually related to the frequency of these modes. N is actually related to the frequency of the light. In fact, it's directly proportional. It's 2 over c, 2L over c times the speed of the light, mostly because it's 2L over lambda. Why did I say the speed? And so, what does that imply? Well, since the object that we want to find is n squared dn, this just gives us, oh, sorry. The object we want to find is 1/8 times 2 times 4 pi n squared dn. What we get is, these cancel out, pi times n squared dn is what? Well, we're just going to get this squared, which is 4L squared over c squared, nu squared. And what's over here? Well, it's just 2L over c d nu. So this is just 8L cubed over c cubed pi nu squared d nu. What we're really interested in is per unit volume, which is just what happens when you divide out the L cubed. Per unit volume, this is just 8 pi over c cubed nu squared d nu. So per unit volume, 8 pi over c cubed nu squared. This is the classical derivation. But there's something wrong with this. You see, the nu squared implies that as frequency goes up, the energy is going to diverge. This is the ultraviolet catastrophe because observations were showing while this hypothesis, the Raleigh Gene Law, was consistent at small values of nu, by the time you got into the ultraviolet range, it predicted a catastrophic divergence that wasn't actually there. So what happened? Well, it turns out we were missing something that was found by Max Planck when he proposed that light's energy is not continuous, it's discrete. As in, light's energy can only be sent and received in packages, like particles. This seemed absurd at the time. Planck himself called it an act of desperation, but saying this was true, and thus that the energy of any light particle was nh nu, allowed him to plug into the partition function from statistical mechanics, and using that, he managed to derive a slightly different formula. 8 pi over c cubed nu cubed divided by e to the, e to the minus nu minus 1. Sorry, nu minus 1. And in the short term, this looks exactly like the original graph, the original hypothesis, since e to the nu minus 1 approximates nu when nu is small. But of course, when nu grows large, eventually the denominator is going to outgrow the numerator, and it's going to plateau and shrink. Hold on a minute, that's exactly what the experiments predict. Max Planck was surprised when he got it down to the letter. But he still didn't understand why this was. It was 1900, but only 5 years later, a breakthrough from Albert Einstein, the photoelectric effect, would change all of that. What Einstein found was that light was knocking these electrons down a certain number of energy levels and wasn't giving anything in return. There was no light coming out, but there was light coming in, which means the light that these electrons were absorbing was exactly enough to get them from one energy level to the next, or from one energy level 2 steps up, or 3 steps up. That is, the light's energy had to be quantized. So this finally showed an experimental explanation for this bizarre phenomenon. The photoelectric effect showed that the discrete model was actually king. The Raleigh Gene Law and the ultraviolet catastrophe were just an indirect showing of what light being quantized actually meant. But the photoelectric effect was really when quantum mechanics was born. Because if light, a wave, could act like a particle in being quantized, why couldn't a particle act like a wave? And so the wave function was born.